So, hi everyone. Thank you for having me again. This is my second time on the platform engineering community webinar, and my name is Abdel. I'm a cloud developer advocate at Google. I work mostly on Kubernetes. If you're probably asking yourself, where have I heard this voice before? It's probably coming from the Kubernetes podcast, which is I'm one of the co-hosts for it. I'm also a platform engineering ambassador and a CNCF ambassador. I do write content around the topic of platform engineering, but specifically on Kubernetes. And today we are here to explore the topic of running agentic AI in Kubernetes from a platform point of view, from a platform engineering point of view. As Sam said, I believe that this is the first time somebody writes about this topic. It is very interesting. I did a lot of research. I couldn't find anything similar. Most of the content I found online is basically centered around tooling. But I wanted to kind of like do a little bit of a holistic overview of why agentic AI on Kubernetes is special and why does it require special treatment. This is roughly the agenda we're going to be talking about today. We're then going to do a quick introduction about AI agents, what they are. We're going to talk about how are they different from regular applications. We're going to see where Kubernetes fits in the agentic AI space. We're going to talk briefly about how you build agents with ADK, Agent Development Kit. Then we're going to talk about the platform engineering side of things. And then at the end, I'm going to just talk to you briefly about what are we doing at Google around agentic AI and how are we trying to make GKE the best place to run agentic AI. So what are agents? When large language models popped up about 3 years ago, it was all about prompts. I think there was probably a time when you heard about this thing called prompt engineering, which is a discipline by which you learn how to write, evaluate, and test prompts to get the most out of a large language model. But then we quickly realized that actually large language models are by definition trained up to a certain point. They have a cutoff date, which means they are not aware of new information. If you go to any random AI agent today, large language model today, and you ask it what's the weather today in insert name of your city, most probably it's not going to be able to answer you because it doesn't know. So typically the way an AI agent will be able to fetch new information is by talking to an API. Another way is this thing called RAG, Retrieval Augmented Generation. And RAG is an architecture that was released by Meta, by which you create a database, a vectorial database, in which you store a bunch of information. And then each time you make a request to the large language model will run a query against the database, fetch a bunch of information, and use that to generate the answer. So that's typically used for things like knowledge base, documentation, stuff like that. And then the example I showed earlier, which is getting access to real-time information, that's typically done through what we call tools. Now, the word tools is a very loosely defined term because sometimes we call them functions, sometimes we call them MCP servers. From a point of view of a large language model, it's just an external endpoint. It could be an API, it could be an MCP server, it could be another agent. So tools are essentially an endpoint that the large language model can query information from. If you put these three things together and then put a piece of code inside these three things, which can function in an autonomous way, you get an agent. And then if you take these things and repeat them multiple times, you get a multi-agent system. So a multi-agent system is composed of multiple agents, and each agent basically has a large language model, a database maybe, and a bunch of tools. So what is an agentic AI? It's an autonomous system, so it can function, reason, act independently. At the core of each agent, there is a large language model. The large language model can be any LLM. It doesn't have to be a cloud-hosted one. It doesn't have to be Gemini or ChatGPT. It could be Claude. It could be Llama 3 running on your own laptop. It could be anything. The large language model is what the agent uses as a brain to be able to orchestrate and make decisions about which tools to call, which API to call, etc., etc. And then each agent has something called an agentic loop, which is how agents work. So an agentic loop starts with the perceive, where the agent collects data about things. So for example, you prompt an agent, that's a piece of data that you give the agent. Then it will think or reason and then plan what to do. Then it will act on that plan, so execute, and then learn from it, store some memory, and then go back to perceive. So that's the agentic loop. So it is an autonomous system that can function without human intervention. Of course, a lot of agents that people are building today, they get triggered by a prompt, but you can also build an agent that will automatically or get triggered on a regular basis and engage in the agentic loop, which is what we just talked about. Now, just from this description, you might think to yourself, well, basically agents are just an application plus a large language model plus potentially a database and a bunch of APIs, right? Surely it cannot be that different than any regular application, because that's essentially what any regular application is. It's code plus APIs that it calls plus maybe a database. So you could just take an agent, package it as a container, and run it on Kubernetes, right? So why are we here today? What are we going to talk about for the rest of the time? Well, fundamentally, they are a little bit different than microservices. And they are different because the computational requirements for agents are different than microservices. And they're also different from the point of view of the communication surface of the agent. The communication surface is basically all the interactions that the agent has to do with the large language model, the database, tools, APIs, etc., etc. This is just a visual representation for you to understand what agents are. Agents normally require runtime. So the runtime could be, in the case of Kubernetes, it's container, but inside that container, there is a piece of code that knows how to orchestrate the agent. Because an agent, when it does the agentic loop and it does the planning phase, a planning could be actually calling multiple endpoints or calling other agents. And so something has to orchestrate all that work. Something has to come in and say, this, I'm going to take this as an action number 1, action number 2, action number 3, etc. Right? An end user will interact with an agent using prompts as a query and then get a response. Then the agent on one side has tools. So those tools can be functions, can be APIs, can be databases, can be external endpoints. And then on another hand, it has a generative AI model, a large language model. The large language model itself can be running remotely, a cloud-hosted one, or can be running locally. Agents has memory. Memory is what allows an agent to actually learn from previous actions. And this memory can be divided into short-term and long-term. Typically, short-term is stored in memory of the agent itself, and long-term requires some sort of durable storage. And then agents might have instructions, they might have system prompts, they might have goals, they might have a profile, they might have tools, they might have policy and governance to kind of control what the agent does. But this is kind of roughly what an agent is, right? So what makes agents kind of unique in the way they are demanding or the way they work? Well, agents can be dynamic and can be also ephemeral. An agent can take an input from a user and then based on that input decide to execute 4 subtasks. Each of these subtasks is a process that needs to be executed independently, and it's typically orchestrated by the runtime. Which means upfront, when you're running an agent, you would never know if it needs 2 gigabytes of memory or 20 gigabytes of memory, because you never know. The undeterministic aspect of agents makes it very hard to kind of estimate how much compute power a specific agent needs. So you need to run your agents on a platform that would allow them to kind of scale up and scale down, or to maybe orchestrate using external tools. And I'm going to talk about that in a bit. They require persistent states for long-term memory. So that could be a database, could be file system, could be anything. They might have a complex workflow orchestration, or they are actually doing orchestration, and an agent's orchestration can be, or an agent can orchestrate a super complex workflow. An agent can also have sub-agents, which themselves are just agents with their own LLMs and their own tools and their own databases and RAG and everything. And the main agent or the root agent might decide on a specific prompt, on a specific task, to actually spin up multiple sub-agents. So to give you a very concrete example, if you have a coding agent, it might have a subtask, which is read files, a subtask called write files, not subtask, sub-agent called write files, another agent which has access to documentation, another agent which has access to maybe an external API, another agent that has access to the entire code base, or that has access to your CI/CD system configuration. And all of these sub-agents will be orchestrated by the root agent for each task that the user is trying to achieve. So sort of the dynamic aspect of how agents work makes them kind of unique in the way we have to set up computing for them. They might have some deep tool integration. So that's the third-party tools, API, external endpoints, etc., which require 2 main things: latency. So you want your API endpoints and your MCP servers to be as close to the agents as possible. And security, obviously. You don't want agents to like go randomly wild and just start doing all sorts of random things and calling all sorts of APIs. You want to kind of control a little bit what they're doing. And then they might need security and governance for their autonomy. You want the agent to be autonomous, but you don't want it to decide to, a very concrete example, you don't want a coding agent to just randomly decide to delete a database, right? So you want to have some sort of governance or some guardrails around which actions the agent can take. This is what Kubernetes fits in. Kubernetes, by definition, has it's basically an infrastructure automation layer, which means if agents need to spin up other agents, we can do them through Kubernetes. You can actually run an agent on Kubernetes that has access to the API server, and then when it needs to execute a task, it can spin up a random pod, ephemeral pod, execute that task, and then kill the pod. That could be one example for why Kubernetes would be a good fit for agents. It's scalable, so if the agent needs more resources, we can just give it more resources. Or we can just spin up more instances of the same agent, put them all behind the load balancer, have some sort of shared memory store across all of them. One thing actually that I remember now that makes Kubernetes a very good fit for agents is the fact that you can now, since Kubernetes 133, live resize pods without restarting them. So if you have a container running inside the pod, you can just give it more memory and more CPU without having to restart it, which means makes vertical auto-scaling very, very quick and very fast. Kubernetes can be set up in such a way that it's highly available and reliable. So you can set up multi-data center clusters. You can set up clusters across multiple zones or availability zones or whatever you want to call them, such a way that you have like a sort of a failover. Kubernetes, since few versions now, since a couple of years, has some really, really good support for device management. And by device management, we mainly mean accelerators. So if the agent runs with a local LLM that needs GPUs to run, then Kubernetes has really good support for that. On top of a newly introduced API recently in Kubernetes called DRA, Dynamic Resource Allocation, which exactly solves this particular problem. And then Kubernetes is multi-cloud, which means you build your agents to run on Kubernetes, which makes them portable. You can just easily move them from one place to another. Few more things that makes also Kubernetes a very good fit for AI is that you can extend Kubernetes with custom resource definitions and operators, CRDs and operators. If you don't know what those are, don't worry about it. You can just think about it as making Kubernetes do more than just applications. You can extend it to do more things, right? And so you can actually build CRDs for agents. You can build operators for agents. Kubernetes is self-healing. This is a very good feature, which basically means if a pod dies, it will just restart it automatically. There are already technologies on the market for doing container isolation for containers on Kubernetes, which means that when you run an agent inside a container, you can make sure that that container is isolated from all the other containers running on the same node or on the same server. There are two main technologies on the market today. There is one called gvisor, which is a Google technology, and there is one called Kata Containers, which is coming from Microsoft. And we are actually working on an open sourcing an agent sandbox project. It already exists on GitHub under the Kubernetes project called Agent Sandbox. And that basically supports both gvisor and Kata containers. And it's designed specifically to run agents inside the sandbox for isolation purposes. You can use a lot of the policy management features of Kubernetes to manage what the agents can do, things like network traffic with network policies, or RBAC for role-based access control, and then obviously observability. You want to know what the agents are doing. There are already like a huge ecosystem of observability tools that are designed for applications that we can just repurpose for agents, and they're designed specifically to run on top of Kubernetes. So very quickly running through some building blocks for running agentic AI on Kubernetes. So you're gonna most probably need to run your agent inside a pod. A pod can be either run two ways, either a deployment or stateful set. Most probably you're going to run a deployment to run a regular agent and the stateful set if you need a database or something like that. You can use any of the auto-scaling features built into Kubernetes itself. Those are the features built into open source Kubernetes to do auto-scaling. Horizontal pod auto-scaling means you can just like add more instances of the same agent. Vertical pod auto-scaling means you can resize the pods to give them more resources. And cluster autoscaler will autoscale the underlying virtual machine layer or the physical layer. So, and then you can also use things like Carpenter if you're running on AWS to basically autoscale the underlying cluster. On Google Cloud, we have something called COCP, Container Optimized Compute Platform, which is basically a cluster autoscaler on steroids. It's a very, very fast autoscaler. You can use jobs and cron jobs. If you need to trigger the agents on a regular basis, you can use a cron to do that, or you can just use jobs to execute like pipelines for the agents. You can use RBAC, role-based access control, for managing what the agents can do. So the example I gave earlier, where you would give an agent access to the API server of Kubernetes so it can spin up workloads on its own, while you want to control what that access do. So you will give the agent an identity and then create a role that has a limited scope on terms of what the agent can actually do with the API server. Because again, you don't want the agent to go wild and start deleting things, right? You can limit network traffic for the agent with network policies, so you can control which agents talk to which agent across which namespaces and which endpoint it can talk to, both inside and outside the cluster. And then Kubernetes has already very, very good support for secrets. You can store things like tokens, API keys inside Kubernetes, and then you have a huge ecosystem of open source tools and commercial tools for doing secret management, for databases, for API tokens, for SH keys, for anything that needs to be stored securely. But before we get to the point of actually running agents, we need to build them, right? And there are basically roughly 4 levels of abstraction for actually building agents, everywhere from rolling out your own framework, if you are crazy enough and you want to do that. You can use some low-level orchestration framework, things like LangChain, which is a Python-based framework for doing large language model integration, or LangChain for J, which is the Java version, Genkit, which is TypeScript. Those can also be built to actually build agents. You have at the level 3, you have something called ADK, Agent Development Kit. I'm going to talk about this in a bit, which basically is a higher level agent-specific framework. It was designed to write agents. It already wraps a LangGraph, LangChain, and a bunch of existing tools, and then give them to you in an easy-to-use framework. And if you want to just vibe code your agent, then you have tools like Agent Space on Google Cloud, and then I'm sure there's other equivalents on other platforms that would allow you to actually vibe code an agent. So go from prompt to an agent. In these levels of abstraction, anything below level 3 can be run on Kubernetes. Agent Space is its own platform. It's a ready-to-use platform, but everything else can be basically packaged as a container run on top of Kubernetes. Speaking of Agent Development Kit, it is a SDK, as I said, written in Python, and also Java, sorry, it's available in both languages, which allows you to basically define agents. It has a built-in dev UI, which is pretty useful for debugging. You just basically run ADK is a Python framework, so you install it. You have a command line called ADK. You can start by bootstrapping an agent by going ADK create, and then you give a name to your agent. It will create a folder with all the necessary files inside, and then you just need to start writing the code of your agent. And then it has development web, which is ADK web, which spins up a web interface that allows you to actually chat with the agent and see what it's doing. It has a lot of logic for building the agent, for reasoning, for thinking, for integrating agents with each other. The example you see on the right is a multi-agent system where we have a route agent that calls a flight agent and a hotel agent. So this is for booking flights and hotels. And then each of these agents has access to tools, which is what you see on the right side. So you have listing customer flights, looking company policy, search flights, blah, 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 search hotels, book hotels, etc., etc. ADK has built-in syncing loops with long-running syncing loops with actually a human in the loop. So if you need the agents to ask a human to validate something before it takes action, you can do that easily. It by default is designed to run with Gemini, but you can actually plug any large language model. You can bring your own models. You can have a fine-tuned model. It doesn't really matter. It by default has support for Gemini, which is the easiest way, but you can actually just instead of using Gemini, you can just use an external endpoint which points to a model that you run somewhere, right? And it has already support for MCP and A2A. So MCP is Model Context Protocol, which is a standard from Anthropic for allowing agents to access external tools. And A2A is agents to agents, which is a protocol for agents to talk to each other. Now, where does platform engineering fit into this story? Well, Kubernetes is complex. And specifically, it's complex for AI engineers. You don't want AI engineers to become YAML engineers. So you need to give them a level of abstraction that allows them to do their work without having to mess with YAML. And that level of abstraction is something what we call usually an IDP, an internal development platform. It doesn't have to be an IDP. It doesn't have to be a UI or a graphical interface. It could be just a bootstrap GitHub repository that you clone and then you start with, which has a template for how you build things, right? What you want is your AI engineers to focus on building the agents and the platforms to run them. So you want to create that sort of easy to use platform where an AI engineer goes from, I download ADK, I build an agent, I click a button or I run one command, I push it, boom, my agent is running. You have to also provide your engineers with a golden paths, with clearly defined paths for how to get from development to production, which should have best practices for security, observability, and reliability. So how do they secure the agents? How do they store the secrets? How do they, if you have requirements for encrypting traffic, how do they do that, etc., etc. Observability, hopefully, so it has already the libraries to do observability. So, and the platform should also have a backend where those observability data will be shipped to, things like Prometheus or Thanos, things like tracing software. Basically, as an AI engineer, I start building an agent, and my code will be automatically instrumented because I am using templates that are already prepared for me. And you want to reduce cognitive load. You don't want people to deal necessarily with Kubernetes because it's complex. So giving people clear paths that reduces cognitive loads and allows them to go to from building an agent to running it is a must, right? In my opinion, this is just, again, my opinion. I'd be happy to be challenged on this. Any platform built for agentic AI has to have, at the bare minimum, the following features. Templates and quick start guides, as I said earlier, like things like how do you bootstrap an agent from building to running, including options to run against local LLMs. So if you don't want your AI engineers to run agents using cloud-hosted LLMs, then you have to give them the option to run those LLMs locally. And running LLMs locally is not as straightforward as you might think it is, because you might require GPU accelerators, you might require like an inference software. So there's like a lot of things that goes into it. If you are curious, I did a 3 hours deep dive yesterday about inference for large language models in Kubernetes in a conference, and it was recorded. It will be published on YouTube. The conference is called DevOX, DevOXX. So you can go look at that to just see how much actually goes into running inference for large language models. The platform have to provide, as I said, tools for observability and tracing. So that's both the client side thing, so the instrumentation side in the code, but also the backends that will receive this observability and tracing data. Third-party integration, maybe a catalog for all the third-party APIs that the engineers can use or can access to, maybe a custom MCP server for your own documentation and knowledge base, anything that your engineers might want to integrate the agent with. And then also a way to integrate policies and governance should be built into the platform. The way I like to kind of sum up these policies and governance is you should always opt for close by default and open as needed model rather than the other way around. So essentially, you should ask people, you should have an environment which is closed by default, and then people should request to talk, to call, to integrate with something specifically on demand, rather than an open by default, and then you run into issues, and then your agent deletes the database, and then you start running around trying to figure out what went wrong. So with that in mind, we have been building GKE for a very long time at Google, for almost 11 years now, or 10 years actually. And we have been doing actually machine learning on GKE for a very long time. Training, serving, development, fine-tuning of machine learning models is not new to us, and it's not new to the industry. So we have really optimized GKE for machine learning models. And today it is one of probably the best platforms for actually running machine learning models in production. Now, agents is just an extra type of workload that we need to support, and we are already doing a lot of work to support it. So at the base layer, we have all the components for the infrastructure that you might need: storage, network, accelerators, etc. Then we have a lot of features for building platforms, things like fleet and team management, observability, accelerators, job management, auto scaling, all that stuff. And then on top, we provide very specific frameworks for doing the end-to-end machine learning lifecycle, including running agents. Everything from interactive notebooks with Jupyter, running jobs with a project called Q, which is open source, optimized inference with things like Kubeflow and Ray, and then now running AI agents with ADK. By the way, ADK actually has support directly for GKE. If you are running ADK locally, you can just do ADK deploy GKE, and the ADK will containerize your agent without having to write Docker file code, and then ship it and deploy directly to GKE for you. One of the key things that people have been having to choose for a very long time, it's not only with Google, right? It's with most cloud providers, is that you have to kind of choose between running your own Kubernetes or using a managed version. And the typical version of, or the typical way managed versions of Kubernetes work is that you manage the worker nodes and the cloud provider manages the control plane. Now, what we have done recently is we introduced something called GKE Autopilot, which is all of GKE without the mess of Kubernetes. It's essentially a fully managed version of GKE. You don't have to manage anything. You don't have to create nodes. You don't have to create node pools. You don't even have to worry about it. All you have to do is you have to choose which type of infrastructure will be created for you based on the type of workload you're running. I will take your attention to this AI here. So if you have a large language model that you need to run, you basically run it with accelerators. You have a specific configuration. We call it compute class. I don't want to go into details, but you essentially just say compute class accelerators, and then we will spin up the node for you. And we have redesigned our stack for very fast auto scaling. So we can actually give you GPU nodes within few seconds, and we can give you regular nodes that doesn't have GPU within fraction of a second. So it's actually very, very optimized for this kind of workloads. So with that in mind, this is all I have. I have few resources for you if you want to go deep dive into the topic a little bit more. One of them obviously would be my article that I wrote on the platform engineering blog called Kubernetes for Agentic AI, a platform engineering perspective. What I just showed you right now is a very, very distilled version of that article. The article is super long and has a lot of details. So I highly recommend you go read it. It's probably going to take you a few hours to go through it. We have a free copy of a Kubernetes for Developers book. If you have never used Kubernetes before, I really highly recommend you start with this book. It's fantastic, written by one of our colleagues, William Dennis. The book is available for free on that link. You can scan the QR code, and I think Sam will send the link later in chat. And it's a free PDF, so you can use it. And last but not least, we are hosting an Ask Me Anything, AMA, on GKE Autopilot on October 15 from 1 to 2 p.m. Pacific time on Reddit. So you can join us there. There will be a bunch of Google engineers hanging out in Reddit, answering all your questions. So please bring your most difficult questions. We like to make the life of our engineers a little bit difficult. And yeah, that's it. That's all for me. That's my link tree if you want to connect with me on LinkedIn. And thank you so much. I hope this was useful. And yeah, that's it.
Yeah, thank you very much. You can't hear the applause. That's the problem with these webinars, but there's definitely a lot of applause in all their own region.
Thank you.
Extremely cool. Extremely cool. I basically already sent the recording before we had even finished the recording to a bunch of my colleagues.
Awesome.
I was like, it's not done yet, but I'm sure this is going to be a great one. So we have 15 minutes now for questions from everyone. So we can just spend a nice 20 seconds enjoying all the applause emojis coming in. You can bask in that for a moment, Abdel. Great way to end the day. But we've still got time for questions. So hey, Dwight, nice to see you. So I like seeing names that I recognize. Best part of a community. Marcus as well. I feel like I know everybody these days. So we'll start with the very first question, which is in the Q&A section, because now the chat is so active, I can't see that question that popped up anymore. So first question from Saibak. Can you please go through one more time in a little more detail how Kubernetes does advanced device management?
Yes. So there are multiple ways Kubernetes does device management. The first project is called device plugin. And the device plugin essentially allows you to manage the GPUs better with Kubernetes, including automatic driver installations. If you want to use GPUs, you need to install the drivers for them. Kubernetes has a way for you to just like automate that whole process very easily, right? So that's the device plugin side. Then there is support for GPU sharing. So if you have multiple large language models that you can actually run on top of one GPU, you can do this thing called GPU sharing, which is slice GPU itself. So you assign time slices of the GPU so you can run more large language models on the same GPU. So you can optimize and kind of cramp more LLMs on the same GPU. And the last thing I'm going to talk about is something called dynamic resource allocation. So very quickly explained. If you have used Kubernetes before and you're familiar with the way the storage API works, the storage API allows you to define what we call a storage class, which defines the type of storage available, SSD, regular disks, blah, blah, blah. And then the developer or the user creates what we call a claim to claim a type of storage, and that will generate volume. DRA functions the same way, but for devices. You can say, me as a platform engineer, here are all the GPU accelerators available in my cluster. And then you would claim a device via a device claim that would basically map your pod or your workload to a specific type of device. So these are three of the examples of how those advanced device management on Kubernetes work.
Nice. Thank you very much. So for people asking questions in the chat, just because we've got quiet and active chat, could you ask them in the Q&A function? So it'll say ask a question or Q&A and you can put it in there. So next one from Joel, or potentially Scandinavian, Yul. So how would you integrate an MCP server with your Kubernetes solution?
Yes. Hi, Joel. I mean, MCP servers are basically just proxies. So I would just treat them as regular containers and deploy them as a regular pod inside Kubernetes. So you can treat them the same way you treat any proxy that you deploy. So the same way you scale your workloads, you can scale MCP servers. The same way you do distributed load across them. So with like load balancers, I would just do that for proxies. They're not for MCP servers. They're not like that different from regular proxies.
Got me right as I went to sip my water. Next question. So a question from Dwight French. If no one here is familiar, Dwight's one of our platform engineering ambassadors as well. So if you're in New York, he's a very fun guy to talk platform engineering with. So from Dwight, do you have an opinion on Red Hat's VLLM and inferencing capabilities?
I'm big fan of VLLM, and if you have any doubts about how serious VLLM is as a project, I was just talking with Sam about it before we jumped on the call. The project's called LLMD. So if you do LLM-D.ai, it's a joint project between Google, Red Hat, and ByteDance, which uses VLLM at the core. But VLLM is amazing. I really love the project.
Nice. So then from another next question from Akshay. And yes, you're right, Dwight. Sorry, I was thinking about PlatformCon New York, where we met last time. So that's where good chance you'll meet Dwight at PlatformCon New York. But if you're in Sacramento, you'll see him too. So next question from Akshay. Does GKE have any L7 policy enforcement? I may want to open up access to S3, but only for bucket A path foo, but not path bar.
Yes. So we have something called FQDN network policies. So those are network policies that are DNS based. So that would be one of them. These are available in GKE out of the box. You don't have to do anything. But they can do DNS based enforcement for which endpoints a pod can talk to, but they cannot do path. If you want to do path, you will need an extra thing. And I am afraid the answer would be a service mesh like Istio. I know that a lot of people don't like service mesh, but for this kind of policy enforcement, unfortunately, service mesh is typically the answer. So out of the box, I don't think that any Kubernetes platform on the market has any support for something like this.
The next question from Roger. Yeah, nice to see you, Roger. It's great recognizing all the names. If you had to build an air-gapped AI sandbox that could process sensitive information, what are the most important concerns people might overlook?
If you want to build an air-gapped AI sandbox that could process, what are the most important concerns people might overlook? I think that typically people, when they talk about air-gapped environments, they tend to focus on the runtime itself without focusing on other things. So you can sandbox the environment where the agent itself will run with, gvisor, kata containers, maybe encrypted, so what we call confidential computing, so encrypting memory and encrypting memory in use. But I would also look at things like network traffic. Is your network traffic encrypted in and out of that sandbox environment? Are your network policies or any sort of like ingress egress policies set up properly to make sure that the agent doesn't, as I explained earlier, go rogue and start invoking external endpoints? What else would be? So network would be one of them. Encrypted storage is the data stored in disks encrypted, including logs data. Are you obfuscating any PII data or sensitive data from the logs? Are you making sure you don't just spit out people's social security numbers in the logs, things like that. So those are the things I would also keep in mind.
Nice. Next question from Siraj. Can a software tester, are software testers able to take advantage of this?
Well, yes. I mean, agents need testing, right? So of course, I would say yes. You need to make sure that you test the agents, because I would say that arguably it's even more needed because of the unpredictable nature of agents.
Yeah, I would definitely agree on that one. There is a lot of room for testing going
Yes.
forward in this AI world. So next question from Nabel. Do you have the price published somewhere for GKE Autopilot?
Yes, we do have a GKE. If you look for Google Cloud Calculator, then you can find the GKE tab, and you can look for pricing in the GKE tab. But fundamentally, GKE Autopilot, the way we charge it for the compute is we charge you for the resources consumed by the pod. So for how much the pod consumes, not for how much the node, what's the size of the node that was provisioned for your pod. But if you go to the pricing calculator, you will find all details there. And we even have I think we added something called profile. So you have a profile for a web application. So instead of having to input how many CPUs, how many memory, you can just say, okay, I have a high volume web application, and then we do some simulation and we tell you roughly how much it would cost.
Nice. Great answer. Oh, and thank you, Jacqueline, for sharing the pricing
Here we
calculator.
go. Yeah,
I was just grabbing it as well. You're much faster than me, Jacqueline. And I think a nice comment from Joe, I'll just read out as well, because I know Joe, so I like picking on people. Autopilot is pretty awesome. I've had a lot of success setting up clients new to Kubernetes with it. So
awesome.
great.
I'm happy, Joe. You should look at two things: COCP, Container Optimized Compute Platform, and Autopilot in standard mode. We just launched it last week. It's amazing.
Nice. Yeah, I think we need to get us in a conference together. Joe is a very interesting guy to talk to, Abdul. So we need to get a conversation going at some point. So next question from Siddesawar. What do you think about the future of AI? Does it replace traditional software engineering?
Typical question when we talk about AI, right? No, it will not replace software engineers, because again, AI is fundamentally just software. I would probably answer with my little bit controversial answer. It would replace mediocre software engineers, because there is a lot of very basic work that if you are a software engineer still doing that work, then AI will replace you. If you are still writing crude applications, then probably you are replaceable. But our industry doesn't tend to replace people as we innovate more. We just have a tendency in our industry to move or shift people from one place to another, typically.
Nice. I think that's the perfect answer to that question. So next question from Rijeng. Hi, I wonder what are the bottlenecks you see in your solution specifically regarding scaling, requests, second, etc.
Yes. So if we're talking specifically about agents and large language models, then the typical bottleneck is there are multiple ones, but the main one would be the type of accelerators that you are using. If the accelerators you are using for large language model are not the right type, then you might not get the proper throughput from your large language model in terms of requests per second or something like that. The second one would be not using the right load balancers for your application, and then you end up with uneven load distributed across your backends, and you might end up having problems with requests and seconds. And the third one would be probably choke points, but those are traditional kind of choke point. Your database is not managed or is not sized enough for whatever workload you're running against it, or you need a cache layer that you're not adding. So some of these choke points or some of these limitations that you talked about are just typical limitations that we are already kind of solved for regular applications. And some of them are kind of specific to large language models.
Nice. Next question from MK. We've got so many good questions in just a little time, so I'm trying to blitz through here. How do you compare SGLang with VLLM from your vantage point?
I think VLLM is slightly more how to say newer or more modern than SGLang. So it has support for more architectures, for more large language model architectures, and also to my knowledge, VLLM the only one has support for this thing called disaggregated serving, which splits pre-fill and decode. And I know I'm going to lose like 90% of the audience when I start talking about this. But if you go to VLLM and just look for VLLM disaggregated serving or pre-fill decode, then you can read more about details. I don't think that that's supported in SLang. And this is actually based on a white paper that Google released a while ago, and then VLLM implements that. It's just like a way to do more efficient serving for large language models.
Nice. And I'm going to grab one question. What? I'll just go for the next one. So from Ramanoj, walk me through the process and the primary Kubernetes objects you would create to achieve this. What are the key components involved, and what are some important considerations like security and traffic management you'd keep in mind?
So I assume that to achieve this means to deploy an agent. So very quickly, a deployment, obviously, a service, and then maybe an ingress or a gateway API would be the three main objects you would use, just regular, like in regular web applications. You might need a config map for anything like profile or configuration. You might need a secret for storing secrets for like API tokens or passwords for databases and things of that nature. And then these are probably the bare minimum that you might need to create. And then maybe network policies for sure. And then any sort of like sandboxing configuration that you might have. If you have like AppArmor or seccomp, then you might want to configure that to kind of make sure that you limit what the agent is doing.
Nice. I'm going to be very cheeky and ask one more question because it's not 7:46 yet. Because I think this question is quite interesting. From Savinda. As agents become more autonomous and potentially self-modifying, how do you prevent an agent from manipulating its own Kubernetes deployment manifests or resource quotas?
That's a very good question. I would not. The easiest way to go about this is prevent the agent from mounting the service account key in the pod. There is a way Kubernetes to do that. And also making sure that the default service account inside the namespace does not have privileged access to the API server. Because the only way the agent might be able to modify its own deployment or its own resource quotas is to call the API server to make that change. So if it doesn't have access to that service account, or it doesn't have the permissions to do these things, then it will not be able to do them.
If only Skynet had thought of that.
Yes. I'll just, speaking of the Skynet reference, just pull the plug. Just turn it off, right?
Just turn it off. That's the solution.
Very easy. Turn off the cloud.
Just turn it off and never look at your cloud bill. Problem solved.
Exactly.
So with that, a huge thank you everybody for joining it. Unplug it exactly, Stefan. So thank you so much everybody for joining. This was extremely fun. You've been a really good group today. Great questions, great chatting. Always nice to see the community vibes. Reminder for everyone, we do these community webinars every week. So we'll have another one next week. We're starting to do some in-person stuff as well on lots of really cool topics. You can find the recording for this session on YouTube already. We'll also send you the recording and we'll send you the slides likely tomorrow morning. If you haven't had a chance to look at Abdel's article just yet, really dive into it. It's a fantastic one, and we'll be sending a platform weekly on that exact topic this Friday as well. But enough from me. Huge thank you, Abdel. This was really awesome. So thank you so much.
Thank you so much.
Here.
Thank you.
And
I'm just
for everyone who has, oh, you go ahead.
Sorry, I was just saying I was leaving my LinkedIn and my Reddit profile in the chat, so feel free to follow up with me in those two places.
Fantastic. And thank you so much everyone for joining. This was really cool. My brain grew 3 sizes this evening. Thanks everyone, and have a great day, great evening, great morning, wherever you are.